Hi, welcome to Real Learning Center. Today we are going to do the last part of rotational motion. We have actually developed an understanding of what is center of mass and why it is important, and we also talked about moment of inertia, which is an equivalent of mass in the case of a rotational motion. And we are now talking about the kinematics of angular motion, and we also will talk about the torque, the new concept, which is equivalent to force in a rotational motion. Okay, so let's just look at some of these basics. Let us say angular equivalence. Let's start with whatever we understand and map it from our regular understanding of a motion. So we are actually very comfortable with a translational motion. Translational motion means a body going from one place to the other place. So now we are talking about rotational motion, where body does not move but it stays in its place but rotates. So what are the equivalents of these two different kinds of motions? And with our understanding of translational motion, how we can also deal with the rotational motion. So that is what we are going to realize. Okay. So let's take the first one. In the first one, you can see that when you basically put a force, a body moves. Okay. And when body moves, we will call basically the change of position. So this change is position is changed from one place to the other place, and that change of position we call displacement. Displacement is change in position. Okay. So this displacement, we are going to give a notation called dx. Dx means change in position. X is position, dx is change in position. So change in position is displacement. Okay, it is just a notation. Okay. Now similarly, you can see here when you apply forces like this, a couple of forces like this, it will actually rotate. So when it rotates, now you will see its initial position was vertical. Now it has rotated and starts making an angle theta with the vertical. Okay, and this angle, what we call, is the angular displacement. That means it is not moving from position to position, but it is changing in the angle. So theta is basically denoted for angular position, and angular displacement is d theta. So the position from vertical to this, it has changed, and the change in the angle is d theta. We call it as angular displacement. Now, if both of them, okay, happened in the time interval, because it takes some time to happen, the displacement or angular displacement, and we call that time, let us say, as dt. Dt is change in time, okay, from time t1 to t2. So what is the change? Duration, dt. Okay, so dt is the time duration during which this displacement has occurred. Then we will actually say, in our regular motion, we will say that your velocity is displacement divided by time, which is dx by dt. It is measured in meters per second, which we already know. Now here what happens in the angular motion, you can see that the displacement here is d theta, which is angular displacement. Angular displacement by time is called as angular velocity, and it is actually measured in radians per second. Angle is measured in radians, okay, not in degrees. So there is a relationship between radian and degrees. It's like how we measure in centimeters, meters, inches, and all that. Here also angle can be measured in various units. The degree is one thing that we know of, and radian is another thing. So there is a conversion factor between them. Okay, actually there is 2 pi radians is equal to 180 degrees, which means that pi means 3.14. 3.14 radians is actually equal to 180 degrees. You can convert it for any radian to any degree and vice versa. So angular velocity is measured in radians per second, and it is also the symbol that is used looks like a small w. You can see it's basically nothing but omega. We call it as omega. It's a Greek letter. Omega is equal to d theta by dt. So in most of these rotational motion, we keep using Greek letters instead of English letters. So there is a tendency for children to basically feel uncomfortable looking at some letters they don't understand. So that is what sometimes makes angular rotational motion a little complex. But don't worry, this is actually just a symbol. So go with basically W. Instead of reading this W, read it as omega. Omega is equal to d theta by d. So radians per second. So now let's go to understand. If the velocity is changing, suppose the velocity is changing, that means that velocity is not constant. In that scenario, you will get into acceleration. And the acceleration is change in velocity by time. So which is A is equal to dv by dt, and it is measured in meters per second square. Similarly, if it is not rotating at a constant angular speed or angular velocity, the angular velocity will be changing. And when the angular velocity is changing, that is omega changing, then we can say there is an angular acceleration. And we will call angular acceleration as alpha is equal to d omega by d. So the alpha is another English as a Greek letter that you need to remember, which is basically instead of A we write acceleration, alpha we write alpha is A in Greek. Okay, so that's why you write it for angular acceleration. It's d omega by d. Now this is measured in radians per second square. So this is quite obvious. So once you look at these angular equivalents, so let's understand the kinematics of the constant velocity. So whenever we talk about constant velocity, that means there is no change in velocity. You see here, when the body is moving, initially its velocity is v. Finally also its velocity is v. Along the way its velocity is just v. Okay. So it is simply moving like this with constant velocity. Then we find out the displacement. Similarly, on the other side we can see that initial velocity is omega, final velocity is also omega, angular velocity. Okay. That means it is all the time rotating with the same speed, rotational speed. So in such scenarios, we will simply say velocity is equal to x by t. Okay. This is like saying that velocity is equal to distance traveled divided by time taken. So it's a common formula, which is applicable only for constant velocity scenario. Okay. Similarly, in a constant angular velocity scenario, you can very clearly see angular velocity omega is equal to theta divided by t. Theta is the angle covered divided by time taken, is angular velocity. So after understanding this, now let's look at basically in this scenario, since initially also it is v, later also it is v, acceleration happens to be 0. Similarly, angular acceleration alpha happens to be 0. But if the angular acceleration or the acceleration is not 0, if it is velocity is changing, then we cannot use these two formulas. So we have to go into a constant acceleration formula. Here, velocity is changing. That means velocity is changing at a constant rate. If it is changing at a constant rate, then we call it as constant acceleration. So we are going to write down the constant acceleration kinematics formulae that we know of and see what do they mean in angular scenarios, that is in the rotational scenarios. Okay, but if acceleration also is changing, that means if the velocity is not changing at a constant rate, okay, initially velocity is going from, let us say, 10 meter to 20 meters per second in 2 seconds, and 20 to 30 in 2 seconds, 30 to 40 in 2 seconds changes velocity, then we call it as a constant acceleration. But if it is changing, 10 to 20 it happens in 2 seconds, 20 to 30 it happens in 1 second, in 30 to 40 it happens in half a second, then it means that acceleration also is changing. So such scenarios we will not address. We will address only with the changing velocity but constant acceleration. Please understand this. If this has understanding of rate of velocity and acceleration is crucial to understanding physics itself. Okay, please understand that. So now, if you see here, initial velocity is u and final velocity is v. So the velocity is changing and displacement also is happening. In such scenarios, you cannot say velocity is equal to distance divided by time, because which velocity, initial or final? So then you use a different formula. So we call it as, in this scenario, let us say acceleration is a. So we'll say velocity is equal to v is equal to u plus at. So this formula we already know. V is equal to u plus, anytime we want to calculate velocity, till that time whatever is the time into acceleration plus initial velocity. That is basically V is equal to u plus at. Same thing is true in the angular case, where omega is equal to omega naught plus alpha t, because we know alpha is equivalent to a, omega is equivalent to v, and omega naught is equivalent to u. T alone doesn't change. T is T everywhere. Okay, omega is equal to omega naught plus alpha. Similarly, displacement x, we give it a formula ut is equal to x is equal to ut plus half at square. We can use the word s or x, the letter. Here we are using x is equal to ut plus half at square. So similarly, angular displacement theta we will call as basically omega naught t plus half into alpha t square. So that is the equivalent. Omega naught is equivalent to u. So hence the formula. So you can yourself write these formulae once you know what are equivalent things. So there is another formula in kinematics that we often use. That is basically relating without t. We will use the distance and the velocity and acceleration. So v square is equal to u square plus 2ax. This formula we use many times in our problems. So similar equivalent formula here is omega square is equal to omega naught square plus 2 alpha theta. Okay. So like 2ax, it is alpha theta. Now once you know these kinematics of constant acceleration, most of the problems of the kinematics kind in the rotational motion can be solved in the same way as in the translational motion. So now let's get into basically force, which is basically cause of motion, force. Okay. So now here, when we talk about force in the regular translational motion, we talk about something called as moment of force in the rotational motion. What is this moment of force? Let's take this bar, okay, and this is basically fixed at there is a axis around which it can be allowed to rotate. So that is this point here, and you apply a force 5 Newton on that, and the distance at which you are applying the force from the axis of rotation, allowed axis of rotation, is what we call arm length, and arm length here is d is equal to 8 meters. In such scenario, if you say, then we define actually moment of force. Moment is not momentum. Okay, it is something different. It is moment of force. Moment of force actually means force into, definition of that is force into the arm distance. Okay, arm length d. So force into arm length d means 5 into 8. It is 40 Newton meter. So Newton meter is the you can use Newton meter as unit. That is the unit for the moment of force. So if you suppose now, if you take that same force and apply it to the slightly nearby, from the nearby arm length, okay, if let us say arm length here is 6 meters. In this case, if it is even if it is the same force, because you change the arm length, now the moment of the force will become basically 5 into 6, which is 30 newtons. It has reduced. You did not reduce the force, you reduced the arm length, and hence the moment of the force reduced. And moment of the force is the one which we call actually the torque. Okay, moment of the force is nothing but the torque, and the torque reduced. So when torque is reduced, its ability to rotate actually also has reduced. So generally what happens is, like you must have, we day to day life we observe this. So there is a door. Okay, the door we open it. How do we open it? We hold the handle and rotate. It actually rotates. So with the same force, instead of putting the handle at the edge of the door, let us say you are taking it at the middle somewhere at the door and pull it. It is harder to pull, because from that point to the hinge, the distance, if you multiply with the force, the total torque you are giving is higher when you are pulling it from the edge. But the total torque you are giving it is lower when you are pulling it from the middle. So, though the force is same, the torques are different, and for rotation, torque is important. Okay, so not just the force. That is why we actually call it as moment of force, which is the another name for the moment of force is torque. So we keep using the word torque, but remember that is nothing but the moment of force. Now, so we know similarly that cause of motion for translational motion is always the force. Force causes translational motion. Similarly, torque causes rotational motion. Whenever you provide the force from the off center, from the center of mass, if you go somewhere else outside the center of mass, apply the force, then it creates a rotational motion. And if you want it to consistently rotate, you need two forces basically. Otherwise, it will rotate and translate. If you just put one force, it will rotate, but it will also move a little. If you put two forces, it causes exactly rotation alone. So torque basically is also called as a couple because it's two forces, couple of forces, and they are acting off center. Okay, they are not acting at the center of mass. So such forces are basically called as such a thing is called as torque. And the torque causes the rotational motion. Okay. Now we need to also understand another term once we get into rotational motion, because we already know a term called momentum. Okay, now what is this momentum in rotational motion? It is called angular momentum. Okay, so angular momentum is nothing but momentum equivalent in the rotational motion. So in the normal regular translational motion, you have mass m and v, velocity of this, and we will call momentum as denoted by a letter p. We will call it as mv. Okay, we generally use a small letter, lowercase letter p, and call is equal to mv. This is momentum. Okay, now if you similarly make something rotate, okay, I have a ball here connected to some point to a rigid rod, and you rotate it. Okay, so that rotation, if you do with the arm length d, actually, then let us say this also mass m, and the velocity with which it is moving up basically is v again. Okay, in that scenario, angular momentum is given as L. Angular momentum is denoted by L. So L is equal to mv into arm length. So that means momentum into arm. So we call it as L is equal to d into arm momentum. D is arm length into momentum. So what does it mean? We actually multiplied earlier, remember, if we multiplied the force with the arm length and we got torque. So it's called as a moment of force, is torque. So multiplying with that arm length is the process where we use the word moment of. The moment of, when we want to use the word, it means you are actually multiplying with the arm length. That is the meaning. Okay. In here again, you can very clearly see angular momentum is nothing but moment of momentum. It is the moment of moment. You take a momentum, multiply it by arm length, so you get angular momentum. So it is the moment of momentum. So these two words are very different, momentum and moment. So don't get confused. Angular momentum is the moment of momentum. Okay. So now let us recap some of the equivalents that we have learned. So we have learned that x means basically our displacement is nothing but position, basically. X is the position and theta is the position in the case of rotational motion. And whenever we say velocity v, omega, which is basically small w, is the angular velocity in rotational motion. Acceleration, when we say a, alpha is the angular acceleration. Similarly, p is basically our linear momentum, regular momentum that we use, linear momentum, and L is the angular momentum, and F is the force that we use in the translational motion, and tau, we call it as tau. That is the torque. Torque symbol is tau. Okay. So this is actually momentum force. So Newton meter. Torque is measured in Newton meter. So this is pronounced as tau. F is equivalent to tau. So there is also a relationship between each one of these individual things also. Okay. So let's understand what is the relationship actually. If r, let us say, is the radius of rotation, because you see the whenever a certain object, okay, is basically making a rotational motion, okay, some particle at the end of the object, that particle is also making a linear motion. Okay. Though it is looking like rotational motion for as a whole object, each particle in that is actually making a linear motion. In the sense, it is moving from place to place. So it has a certain velocity. Okay? It has a certain position. So if you want to relate those positions, that means linear velocities, linear position, and linear momentum to the angular momentum of the whole system. Okay? So how do you relate it? So you relate it by basically saying x is equal to r theta. Okay? So this is L is equal to r theta kind of thing. For a circle, any length in the circle, length of the sector, that line, arc length in a circle will be actually equal to the length of the is equal to the radius into the angle subtended by at the center. So this is actually a regular geometrical statement, x is equal to r theta. So now if you actually do one level further, then velocity will be actually equal to r omega. Velocity is nothing but x by t and theta by t, so will become r omega. Similarly, a is equal to r alpha. So like that you can simply multiply and the r and get all the linear equivalents. Okay. However, here you can't simply multiply. P is not like LR. It's not correct. Okay. So in the case of momentum, in the case of a moment of a force or a moment of a momentum, we have a different form. We know that L is equal to R into P. That means my arm length into P. Here L is equal to R into P. And it is also tau is equal to R into F. So here always in the first three you can see linear comes on the left side and angular comes on the right side. And in this only, angular comes on the left side and linear comes on the right side of the equal sign. And R is also always there for multiplication. So this is basically how you have to recap and remember these equivalents. Now let's look at one more concept called as conservation of angular momentum. So we know the conservation of linear momentum. What do we know? What is the meaning of conservation of linear momentum? Let's say, assume that there is a ball which is continuously moving in free space with a velocity v. Okay, so it's continuously moving. Unless somebody disturbs externally, it will not stop. It will keep on moving. Its velocity does not change. So if there is no force, momentum mv does not change, because you know velocity does not change as per Newton's first law, and m does not change generally. Okay, so mv does not change. That means if there is no force, mv remains same. This is what we call conservation of linear momentum. So conservation of linear momentum is quite simple to understand. It is same as Newton's first law. So let's look at the scenario of a rotational motion. So let us take two masses connected by a rigid rod with less negligible mass, and let us say this is m by 2 and that is m by 2. So totally m, the total mass, and this radius, let us say, is rotational radius, although it is r. Okay, in such scenario, if you actually rotate, so then what happens is you can calculate the angular momentum of this. The angular momentum of this is simply equal to, okay, L is equal to R into, okay, V into m by 2. So mv is momentum. Okay. Here in this case, m by 2 into v is momentum. Momentum into arm length r. So r into v into m by 2 is the momentum, angular momentum of one of the objects, and the other object is another m by 2. Add together, you get r into m into v. R into m into v is the angular momentum of the whole system. Now, if there is no force, this angular momentum L does not change. Okay, that is basically conservation of angular momentum. So, if there is no force, if there is no torque, because in rotational motion we talk about torque. If there is no torque, L does not change, and this is called conservation of angular momentum. No big deal about it. It is similar to the conservation of linear momentum. However, there is one small catch here. Okay, this angular momentum is a multiplication of three variables, r, m, and v. Whereas momentum is a multiplication of two variables, m and v. Okay. So in the case of linear momentum, we know very well that any time mass doesn't change. So whenever somebody says that linear momentum is conserved, simply we can say velocity is constant, okay, which is Newton's first law. Here, whenever we say angular momentum is conserved, can we say that R into V is always constant? We can. Okay, R into V is nothing but but if you change the R, the V changes. Remember this. If you change the R, V changes such that R into M into V remains constant. So L remains constant. If you change R, then what happens? V changes so that L remains constant. So conservation of angular momentum is more trickier. L remains constant, not just V. Okay. L is nothing but R into V. Now, R into M into V. So to keep L constant, you have to, if you change the R, V will change. So you see an example, for example, here. I will basically take a scenario where the distance between them I am changing. Okay, but it is rotating freely. The moment you change the distance between them, if it is made nearer, automatically the speed of rotation increases. So whenever actually it goes farther, speed of rotation decreases. That is because angular momentum remains same all the time. And this is even more pronounced in the case of angular momentum conservation in elliptical orbits. When Earth goes around the Sun, okay, in an elliptical orbit, when it actually goes nearby, it speeds up. You can see, it speeds up when it goes nearby, slows down when it is far, speeds up when it is nearby. What does it mean? That means whenever the R is small, V will increase. Whenever the R is big, V will decrease, such that the combination of L and R remains, L, R and M remains constant. So this is also stated by Kepler's laws, which we will study in gravitation. Okay. This is an example of angular momentum. So now if you see other equivalents, finally to understand basically the rotational motion, Newton's second law. So Newton's second law is F is equal to ma, as we know, but its form in the rotational motion is tau is equal to I alpha. You can clearly see m here is equivalent to I there. Okay, tau we know is equivalent to F, alpha I know is equivalent to A. Okay, m and I are also equivalent in the sense that it is not equal. Equivalent means they take the same place, okay, in the rotational motion. I is moment of inertia that we have studied in the last session. So tau is equal to I alpha is basically the formula of Newton's second law in the case of rotational motion. Similarly, the Newton's second law has an alternate form, which we say rate of change of momentum is force. That means dp by dt, change in momentum divided by time, is nothing but force. So similarly, Newton's second law, if we want to state using angular momentum, dl by dt is tau. So rate of change of angular momentum. dl is a change in angular momentum, dt is the time. That is this Newton's second law, alternate form. Now there are also a few more things like kinetic energy. We know kinetic energy is half mv square. What is its equivalent? You can yourself write actually half I omega square, because for m it is I, for v it is omega. So similarly, we talk about work done. So in work done, we talk about force into the displacement distance. Yeah, displacement. Here work done is torque into angular displacement. So like that, you can actually have equivalents of all the things that we have studied in the rotational motion. So when you do some problems, it gets much more concretized in the head. But this whole of this session is important. Remember all these things. They are a little more to remember than other sessions, but they will be useful if you practice. So that ends our basic concept videos of rotational motion. And let's come back for another topic in the next video. Thank you.